Hello and welcome. Today we're going to talk about heaps. Heaps are an interesting data structure that's not used too often, but is used for a pretty narrow category of problems where they are very helpful. Heaps are often also called a priority queue instead, although you can implement priority queues with other data structures. Heaps are called priority queues because they're used in situations where you want to take the most important item out in O of one time, or at least look at the most important item in O of one time and remove it in O of log n time, basically. We'll see why, obviously, as we go later on. So when do you want to remove the most important item? When do you want access to the most important item? And you don't care about having access to the rest of the data structure. Well, if you have, let's say, a bunch of customers, and your customers have some kind of value from 0 to 999, well, if a customer with the highest possible value, which depends on how you want to phrase it, maybe the customer with 999 is the highest, maybe smaller means better, maybe the customer with 0 is the highest, either it's a priority or a rank, but okay, let's say the customer with 999 is the highest priority. Well, if they come in, it doesn't matter how many other customers you have waiting in the pool to be served by your application, you want to serve that customer with 999 first. So they jump to the front of the queue, they get served next. That's why we call it a priority queue. Now, if you want to get access to the maximum, the largest item, then you're going to create a max heap. If you want to get access to the smallest item, you're going to create a min heap. If you want access to both, you can always create two heaps. You've got to do everything twice. The insertions and the removals all have to happen twice in that case, and it's difficult to maintain two heaps for some reasons that you might understand as we go through this, but it's a possibility if that's what you want to do, if you need access to both the max and the min. But generally speaking, we do one heap, and we get access to either the largest or the smallest item in a data set in O of one time, and we get to remove it in O of log n time. So pretty similar to a binary search tree's performance. Okay, heaps are also a kind of binary tree, like a binary search tree, but they are not a binary search tree. They're just another kind of binary tree. So every node has a left and a right child. And let's get into the visuals. And we'll see, whoops, that's the homework. Let's get into the visuals of the demo. Where's my lovely heap demo? There's my heap demo. There we go. So in the visuals here, we're going to see that I've decided to represent it this time as a bunch of squares. Now you got the root here, you've got the root's left and right child, there's this node's left and right child, there's this node's left and right child. Once you get into these tiers further down, it can be a little bit difficult to conceptualize. I'm going to fill this with a bunch of the same values so that you can see a couple of things. So I just filled it with a bunch of 65s. First of all, I represented the heap as an array. Heaps are almost always going to be represented as arrays under the hood. And that's because heaps don't have any gaps. Items are always going to be inserted without gaps in order. The only gaps you're going to see are going to be at the end, so in the unfilled portion. But that still doesn't impact their ability to be called a complete tree. There was a complete tree. And using an array is also easy to do because unlike binary search trees, we don't have to move entire subtrees of the heap around. So when we were removing a node from a binary search tree, like for example when we removed the root of a binary search tree and it didn't have any right children, the entire left subtree had to shift up. That meant all the items in the left subtree had to move around within the array. And that's very annoying to implement. Since subtrees never move in a heap, we'll see that they don't have to. It's a lot easier. There's none of these weird, inconvenient edge cases to handle involving using an array. And so you'll almost always see heaps represented under the hood with an array. You could also use an array list too, or you could simply use an array and then copy it over when the heap gets full. That's another approach. So unless you do that, of course, some of this empty space at the end of the heap is obviously going to be wasted. If you do represent the heap as an array, of course it makes sense to use a power of 2 for its size, because in every tier of a binary tree you've got 1, you've got 2, you've got 4, you've got 8, you've got 16, you've got 32, you've got a power of 2 nodes in every tier. So in this case I made my heap 64 items big, so the last tier here is 32. Alright, so with all of that in mind, let's clear this out and get into some of the operations. We'll start with inserting. items into the heap and see what that looks like. We'll see that I'm going to be displaying the minimum over here in the top left corner, but it's always very easy to access the minimum. It's always going to be the item at index 0. So today I'll be building a minimum heap, and that means that the root is always going to be the smallest item. The other kind of heap, again, max heap, where the root would be the largest item. The rules are all the same, just whenever I say bigger, say smaller instead. Whenever I say smaller, say bigger instead. And otherwise, everything implements the same. All right, so I'm going to insert a 90 to start. There we go, it became the root, lovely. And then let me insert, you know what, let me start with a smaller number. 90 was too big. Let me start with an 89. And I'm going to insert something bigger, and we'll see that, first of all, it's going to get inserted onto the end in the next available spot. And second of all, that nothing happens because, well, 90 is bigger than 89. Heaps have basically one rule, and one rule only. Since this is a min heap, the root of every subtree has to be smaller than all of its children. So 89 is smaller than 90. The rule is preserved. If I add another thing, again it adds on to the end. I add an 89. 88 is smaller than both 90 and 89. The rule is preserved. No issues here. Okay. Another thing that I had said earlier was that the root has to be smaller than its children. Well, I actually omitted something here. It's smaller than or equal to is also fine. So here I added a couple 90s, and that's perfectly fine because 90 is equal to 90, obviously, in size. If you remember back to when I talked about representing a binary tree as an array, there's also a very quick way under the hood to tell what the left and the right child of any given node are if you know the index. So for example, the node that's at index 1, if we wanted to find its left child, all we would have to do is find the item at index 2 times 1 plus 1, which is 3, and the right child is 2 times 1 plus 2, which is 4. So to find the left and the right child of any given index when we're representing it as an array, do 2 times n plus 1 or plus 2. Okay, let's look at something more complicated then. Let's try to insert something that is smaller than 89 and see what happens. So I'm going to insert something that is smaller than 89 and see, oh, okay, I accidentally inserted 89 itself, all right. Well, next time let's insert something smaller than 89 and see what happens, all right. So you would have expected the 88 to get inserted here, and you would be correct. The 88 was supposed to insert there. And it did. But then what happened was we compared it against its parent. And remember that the rule of the heap is that every child has to be bigger. The rule of the min heap, at least, is that every child has to be bigger than its root. And in this case, that rule was violated. So what we did was we swapped their positions. We swapped 88 and 89, and 88 ended up in this spot instead. Now the rule is back to being enforced. So you can imagine what happens if I insert something very small. Well, it's going to end up following that same process where it swaps, and it's going to do that repeatedly until it reaches the top. So here I'm going to insert 5. You can follow along in the console for the order that the steps went in. So 5 got inserted over here at index 7. Of course, the item at index 3, its parent, was bigger, so they swapped. The 5 swapped with the 90 at index 3. And then the item that used to be at index 1, used to be a 90, rewind the video if you don't believe me, it swapped with that one. And then the item that used to be the root, the 88, was obviously bigger too, and so it swapped with that one. And through that series of swaps, 5 ends up being the root. Let me try again to insert another number. I'll insert a 4. The 4 got inserted onto the last spot there at index 8. It swapped with its parent, then swapped again, and then swapped again, and ended up as the root. You notice that it kind of propagates up. That's why we call it bubbling up. We always start at the bottom. We insert into that very last spot. You can also think of that spot as the size of the heap, so you can always get the last available spot by calling size, similar to array list, right, where ArrayList.size gives you the size of the array list, but it also gives you the next available empty spot at the end when you insert something. Same thing with the heap. always bubbling up in the subtree at the end where we insert it into. So if I insert, let's say, a 6, 6 doesn't have to bubble all the way up to the top. It only performed a single swap because 5 is already smaller than 6. If I insert a 7 here, it doesn't have to do anything at all. It just stays there at the end because 6 is smaller than 7, and 7 is the right child of 6. So 6 has left child 90, right child 7. Remember, index 4 times 2 is 8, plus 1 gives us 9, plus 2 gives us 10 for those left and right children respectively. All right, let's do one more insertion for practice. Let's do a 2, swapped with the 88, swapped with the 89, then swapped with the 88, and then swapped with the 4 to become the root. See if you can figure out what's going to happen if I insert a 1 here. So 1 is the right child of 5, right? 1 is going to be the right child of 5. So what's going to happen? It's going to swap, index 5, value 88. It's going to swap with index 5, value 88. That means 88 is going to end up here. And then it's going to swap with this 4. That means the 4 is going to end up here. The one that was in index 2 will move to index 5. And then it's finally going to swap with the root, the one at index 0, the one that has a value 2. The 2 is going to end up right there. So we're going to end up with 2, 4, 88, and then that 1 that we inserted will end up at the top after bubbling up. And there we go, 1, 2, 4, 88. All right, so hopefully you get the idea when it comes to insertion. And hopefully you see that in the best case, like when we inserted the 7, it can be O of 1 when no bubbling up has to happen. But in the worst case, it can only be O of log n. It only takes as many steps as the tree is tall to bubble it up to the top. And since this is a complete tree, its height is always log n. When we said that binary trees had a best case performance of log n, we were talking about like best cases or average, because binary trees could become unbalanced, right? One side can become much larger than the other, and it can become taller than it's supposed to be. But a heap is always going to be complete, and so it's always going to be perfectly balanced, and its height is always going to be log base 2 of n. So there's 13 nodes in this heap. Log base 2 of 13 is 0, 1, 2, 3 tiers tall if you round down to the nearest integer. So if we added a couple more nodes here, eventually we would get to the point where log base 2 of 13, 14, 15, 16, 17, 18, 19, anything beyond 13, 15, 15, anything beyond 16 will be log base 2 of 16 and up will be 4 until we get to the 5th tier, and so on and so forth. And also remember again that there's 1, 2, 4, 8, 16. There's a power of 2 nodes in every tier. Okay, so that's insertion. It's O of log n because in the worst case we have to bubble up the height number of times to get to the top. Now we have the smallest possible value here because I didn't do any negative numbers, so one's the smallest item, it's the minimum. What happens to remove it? How do we remove the smallest item, and then what happens? So I'm going to open up good old Paint to do the demo here. The Windows key is 524, so it added a 524 to the end here. And I'm going to draw this out as best I can, and then we'll follow along to see what happens when the minimum is removed. You can also think of removal as the process of finding a new minimum, right? Because after the minimum is removed, what has to happen is that we have to find a new minimum to take the root's place, since remember the root is always the smallest item in the tree. There's a few 90s here. 7. 89 is 4 is left child. 88 is 4 is right child. Okay, weird. I ran out of space there apparently. And 524 is 89's left child. Okay, so when we remove that 1, we have to decide what's going to take its place. How do we rebuild the heap? And obviously we're not allowed to have gaps, so we have to fill it in with something. And it has to continue to be a valid heap, so every subtree, the root is always the minimum still. That's the rule we need to try to enforce. So you might say, let's replace it with the 2, because the 2 is obviously the minimum, and it's obviously going to be one of the children of the root that is the minimum, because these are going to be like the next 2 smallest items, you might say. Well, maybe, yeah, that's true. But if we replaced it with the 2, then we would have to find something to move up to take 2's spot, and then let's say we replace 2 with the 4, then we have to find something to move up with the 4 spot. We're going to end up actually doing a lot of swaps. Instead, there's a cleverer but sort of counterintuitive solution, and it's to replace it with the last item. In this case, the last item is quite large. It's 524. And once we've replaced it with the last item, the item at the last index, the item at index size -1, we start a process called heapifying from the root on down. So we heapify first at the root at index 0, and that means that we figure out which of the 2 children, left or right, is smaller, and we execute a swap. So 2 is the smaller child, 2 is going to take 524's spot, and they're going to swap. Okay. Now we recursively heapify at the destination. So the destination of the swap was over here, 524 ended up there. We're going to heapify one more time. Which one is smaller? Well, obviously 4 is smaller, so 4 takes... Something is wrong with my mouse today. 4 takes 524's spot, they swap. And we're going to do it again, recursively heapify at the destination. So 88 is the smaller item, and 524 ends up there. By virtue of the item we happen to be swapping this time being so big, 524 is obviously a very large item, we had to swap it all the way down to the bottom. Since 524 is very large, it's always going to swap all the way down to the bottom, because actually the maximum item here. So this kind of presents a worst case example. But let's see if this is correct. Let's see what happens. So I'm going to remove that 1. And what we've ended up there is indeed what we thought we would get. We got the 2, the 4, the 88 being 4's left child, and then the 524 is now 88's right child. Okay, so let me do it again, but I'm going to insert a node so that we're not swapping 524 on down. Now let's insert another 90. Okay, 90 is obviously not the largest in the tree, but there are not a lot of numbers bigger than 90 in here. Okay, so if we were to pop the minimum again, 2 goes away, and then we need to re-heapify. We take that last item, the item at size -1, put it as the root, heapify. That means that 4 is going to take 90's place. 90 is going to take 4's place. Ta-da. Heapify again at the destination. Well, 88 is the smaller of the 2 by just a little, so 90 is going to take 88's place, and vice versa. And 89 is the smaller of the 2 down here, so 90 is going to take 89's place, and vice versa. Voila. Execute again, and we see that the tree is indeed in the state that we expected it. Okay, so how many steps does removal require? Well, popping out the node, the root, that's O of 1, and then in the worst case, in order to heapify and propagate that replacement on back down and then find the new minimum, it always takes us, just like for insertion, logN steps, proportional to the height of the tree. So you only have to execute, at most, in this case, 1, 2, 3 swaps to get down to the bottom. So once again, the worst case for removal, as well as for insertion, is O of logN. And in the best case, it might even be O of 1, or not O of 1, but O of a small number if you don't need to execute as many swaps. So O of logN is the worst, but you could do better in some cases and not have to do any swaps or have to do a minimal number of swaps. Let's do one more example, but I don't want to do an example with 524 at the bottom. So let me rig it for a second, and let's do another example. So let me do 987654. Do small numbers so that I don't have to rewrite a lot over here. Alright, so 2, 6, 4, that's 9, 7, 8, and 5. Alright, so if the 2 gets removed, then the last number is going to take its place again. The last number is just literally the last in the array, the one at size -1. The last number took its place, that's 5. How many swaps are needed in order to reheapify this? Well, 4 is smaller than 5. There we go. 4 is smaller than 5, and now we are done. No further heapification is required because 8 is already larger than 5 is. This is already a valid min heap on this side. Let's see that that's true. So when I remove 2, we see that that's not right. 8 ended up swapping with 5. Looks like there might be a defect when I restart it. Yeah, that's not great. So let's do that one more time, starting from this state. And hopefully I'll fix that later. So I've got my state like this. When I remove the minimum, which is the 5, 7, it's going to take its place. There goes 7, and then it's going to heapify. 6 and 7 are going to swap, because 6 is smaller than 7. And at this point, hopefully it doesn't bug, well, we're done. We only had to do one swap, because 7 is already larger, or 9 is already larger than 7. Ah! Bugged again. Okay. Should have tested my demo better beforehand, but it should have been like this with 9 at the bottom. So what I ended up doing here was heapifying some extra times after I no longer needed to continue swapping. Okay, so removal is logN in the worst case, but it is sometimes better than that. Sometimes you can stop heapifying earlier on. Again, demo broken, but the version in Paint that you see there is accurate. So that's what it should be versus what the demo shows. Okay, so logN for insertion, logN for removal. Now let's look at what the plan is for the homework. So the homework is a game of Snake with a heap off to the side. You can press the space bar to pause, and then press space again to resume. I'm only going to show you one color of apple, but you have to program some others. So when you eat a red apple, you get a random number added to the heap. And instead of the minimum, I'm showing the average in the top left corner there. That basically is like your score or something. You're trying to get the highest average you can. Then that's easy to do because when you eat another color of apple, it's going to be a green one, it'll knock out the smallest item in the snake, which is actually also the minimum of the heap. So we'll knock it out from the heap, but also from the snake. I bound it to a key here, so I can cheat. I'm going to show you what happens when I push it. The 11, which was the smallest item in the heap, is removed. If I push it again, then the 16, which was the smallest item in the heap, gets removed. I push it again, that 21 that I just picked up goes away. And if I push it a bunch of times, I can eventually empty out the heap and turn the whole snake black, so all of its segments are now dark. The segments that are dark are immune to getting eaten, so the snake can pass through those freely. When the snake passes through a part of itself that isn't dark, so if I eat my own tail like that, the snake dies, the heap gets emptied out, and the game starts over. Or, well, the apples stay there, but the snake starts over at one segment big. So the goal of the game is kind of to pick up as much score as you can, keep your average high, get rid of the segments, and pull off some cool tricks while passing through them. Not a particularly challenging game. You should always basically just remove all the segments that you have except for the biggest one, and that gives you the biggest average all the time, so it's not exactly difficult to win, but there you go. That's the homework. So adding nodes, removing them, and tracking two data structures at the same time. The snake, of course, is a linked list, while the heap on the right-hand side is, of course, a heap. Okay, that's it for heaps. Hopefully you enjoyed that, other than the glitches in the demo. And I will see you next time for another exciting data structure or algorithm.